we proceed onward with more review and new stuff in Chapter 19. There's a really wide variety of topics in this chapter. Some of them are honestly review, and some of them are new, and they all have to do with synthesis, making new molecules. So this part that we're going to dive into here is the kind of the third part, which is revisiting of ways to reduce carbonyls down to CH2s to the methylene group. And we've already seen part of that in the realm of the Wolff-Kishner. So now we're going to learn two new reducing methods, the Clemmensen reduction and the use of Raney nickel. And that'll probably make for a pretty short mini lecture. I think I will save protecting groups and selectivity to our next mini lecture. So, quick review of Wolff-Kishner. You already know that it's something that can basically tear off that carbon-oxygen double bond one way or another and give you a CH2 in its place. And it's a pretty cool little reaction. It's fun to watch. You get nitrogen bubbling off because you first form the hydrazone. That's why we saw that in Chapter 18. And then the hydrazone undergoes deprotonation. Okay, so you can imagine the first step here. Eventually we lose water. And then, under these conditions of strong base and heat, you may recall that the base deprotonates, puts a negative charge here, etc., etc., etc. You can review the mechanism in Chapter 18. The problem with the Wolff-Kishner is, holy moly, these are mean conditions. I mean, you're basically boiling your compound in concentrated sodium hydroxide. So if I think I'm going to be able to use the Wolff-Kishner to reduce this carbonyl in the presence of this nice electrophile that would very happily undergo a reaction with this strong nucleophile, no way. So the good news is there are different ways we can reduce CO double bonds down to CH2s, one of which is the Clemmensen reduction. So here's an example, an extremely recent example of the Clemmensen reduction. This was just published in 2014, in February of 2014, on February, I think it was February 14th, maybe. I don't know, but it was just very recently published in a route towards this interesting little beastie. This guy is called diberylane, and you may look at it and think, what's up with that molecule? A lot of times we make new molecules just because of the challenge of making them, but it turns out that along the way you often develop new methods that turn out to be very valuable. So this one's obviously a pretty neat looking symmetric molecule that has some inherent molecular beauty. I'm not making this up. We really do talk about beautiful molecules. But anyhow, so here you can see we've got plenty of things that need to be reduced off or gotten rid of before we can get to diberylane. And here you see the reagents for the Clemmensen reduction. Basically, you dissolve zinc metal in liquid mercury, and that's called an amalgam. So you take your zinc amalgam and concentrated HCl, put it in toluene. Well, toluene boils at 110 degrees. You're heating this in boiling toluene, and that pretty much blasts off everything but the carboxyl group here. It does, in fact, even cleave the ester to give you the acid. I'm not showing the rest of the chemistry that takes off the carboxylic acid group, but you can see that the Clemmensen works in decent yield to reduce my ketones all the way down to the CH2s, and that's its primary use. It happens to also have removed that hydroxyl group, but that's not what the Clemmensen is typically used for. In any case, you can see that the Clemenson is kind of just the opposite of the Wolff-Kishner. It's strong, harsh, acidic conditions. So needless to say, if I think I'm going to carry out this kind of reduction, removing the CO group here and keeping the double bond intact, not a chance. So for this one, the Wolff-Kishner would be a good choice. Because, of course, this is a nucleophile, and the Wolff-Kishner is full of nucleophiles. And nucleophile plus nucleophile equals no reaction. The Wolff-Kishner will take this out just fine. The Clemenson would take out both the carbonyl and the double bond. Then there's one more method that we'll look at in Chapter 19, and that's called the Raney-Nickel method. The Raney-Nickel method basically is 2 steps. First, you add a dithiol, this guy right here, to your aldehyde or ketone, whatever it is you want to reduce. And that forms a thioacetal. And I'm not going to go through the multiple steps of the mechanism, but just remember that this is Chapter 17 chemistry, as I recall. So it's catalyzed by acid. It may be a protic acid. It may be a Lewis acid like BF3. No matter what the acid is, it gives you this thioacetal. And then Raney-Nickel is literally nickel. It's a nickel catalyst that's kind of like a sponge. And you'll see that I haven't actually said that there's hydrogen gas here too. There is very much hydrogen gas there, but it comes in with the Raney-Nickel. We'll see some reactions later on where we actually have to have a tank of hydrogen bubbling through the reaction mixture. But this, the hydrogen, is actually just part of this reagent, and what we get is, as you've seen, complete removal of the CO double bond and conversion down to the alkane. So both these last 2 mechanisms are in the realm of organometallic chemistry. You'll notice that we did not say anything about mechanism. Well, and we're not really going to say much about mechanism. I will only say that in the Clemenson reduction, it is believed that there is some kind of zinc carbon bond that is then that's like an organometallic, right? Kind of like CLI or CMGBr. So it's believed that somehow or other the zinc coordinates to the carbonyl carbon, and then that gets protonated a couple of times to give you the CH2. And the only mechanism you need to know with the Raney-Nickel one is simply how the thioacetal is formed, and you already know that from Chapter 17 and 18. So the nice thing about the Raney-Nickel reaction is that it's really super mild. No harsh acid, no harsh base, no high temperatures. So it can be used in a variety of cases. How about this case? Will this reduction work? Well, here's an example where the Raney-Nickel reaction is not going to work at all, because we know that the aldehyde is invariably more reactive. So there's no way I am going to be able to get this dithiol to react here and then reduce here to give me this product. Instead, everything's going to happen here because the aldehyde is more reactive than the ketone. So that means we have to have another way to make this kind of chemistry happen, and that takes us into the realm of protecting groups and selectivity. So this is truly a mini lecture, and I'm going to stop it here and save the protecting groups and selectivity for our next exciting installment. But before I do that, I have an exciting joke, but of course, and it's so nerdy. I love it. Basically, a small piece of ice, a little mini iceberg, lived in a test tube. Well, this poor thing, it fell in love with a nearby Bunsen burner. "Bunsen, my flame! I melt whenever I see you," said the ice. The heartless Bunsen burner replied, "Relax. It's just a phase you're going through." Ba-dum-bum. I tried to warn you. It was really bad. Kiddo. That's all for now. Soon to see protecting groups.